here we're returning to the microcosm, the semiconductor industry, which really has shaped all my explorations of technology over the decades. And throughout this time, I have been partly preoccupied with a scandal at the heart of electronics. Here we are, we've elaborately, by an enormously complex process of thousands of steps, we imprint wafers with hundreds of microchip dies, and then we scribe them apart and we send them to islands in Asia to be packaged into microchips and then reassembled back together in other factories as unprinted circuit boards, most of which are occupied, despite the 0.3 nanometer dimensions of the geometries on the chips, by all the apparatus that feeds the chips, all analog devices and that interconnect with the real world. So, now for the first time in decades, there's been actual progress made in what's called wafer-scale integration. And the biggest breakthrough so far is Cerebras, and Sean Lee, okay, is a co-founder and chief hardware architect at Cerebras. His boss was supposed to come, but got detained. So Sean, we get the actual guy who's the hardware architect here, which is maybe an upgrade. So he thinks so. Oh, good. Okay. So we got the actual man here, and welcome to Sean Liu.
I'm Sean. I'm the chief hardware architect and co-founder at Cerebras. On the schedule, you will see Andrew Feldman. He's the CEO. He's sick today, so I'm Andrew today. As was already introduced, we're all about Waferscale. So let me first tell you a little bit about us as a company, if you're not familiar. We started a few years ago. Now we have over 300 engineers, and we have customers and engineers all around the world. And we set out with the mission to drastically change the landscape of compute for AI. And as I'm sure all of us know, the last few years has been a crazy ride for AI. And so it's been pretty crazy. But I'm here today to talk to you because we're only at the beginning of artificial intelligence and neural networks, and we're already at a pace that traditional methods can't keep up. In 2018, we had models, neural network models with a few hundred billion parameters, and now, just a couple of years later, we have neural network models with hundreds of billions of parameters. Just a couple of weeks ago, Microsoft announced a 500 million parameter neural network that they call MTNLG. That's 1,800 times more compute in just 2 years. Right, let me repeat that. 1,800 times more compute in 2 years. That's completely unprecedented. And all of these ML labs are talking about running multi-trillion parameter models. So that, as a technologist, is both exciting and it's daunting. The exciting part is, as an industry, we've been making some substantial improvements over the last several years. We've been improving process by going from 16 nanometer to 12 nanometer. Now 7 nanometer chips are used everywhere. We've been improving memory technologies with high bandwidth memory, exotic silicon interposers. We've improved in precision, lower precision numerics. And lastly, we've as an industry, created innovative data path designs, such as systolic arrays. And all of these have helped drive that capability that I just showed you, that's giving us all these larger and larger neural networks. So let's look at each one of these. On the process side, Moore's law is not dead. In the last 10 years or so, I plotted the transistor density for the largest GPU, and as you can see, it's alive and well. And we see this continuing for the next several years at least. Everything else I'm going to lump into a category I'm just going to call architecture performance. So this is the amount of performance you can get per transistor. And what's cool here is that this, again, is for GPUs over the last 10 years. There's a very steady increase. And so this is all very, very exciting. The industry is moving along all these axes. And the architecture of these designs really matters. So that's the exciting part. In the last couple of years, we got 2 times process improvements. We got 3 times in architecture improvements. But now comes the daunting part, right? I just showed we as an industry, as an ML industry, are looking for something on the order of 1,800 times. And we produce 6. And so that's the 300 times gap that in the last 2 years has been completely filled with system scale-out. Here's a picture of Google's TPU in their data center with thousands of chips. Now, that's great, right? That's what enabled all of these models I showed at the very beginning, but it's not sustainable, right? We got here in the last couple of years by relying very heavily on scaling out to many, many chips in the system. But we can't keep repeating that, because that would mean just in the next couple of years, we would need on the order of 100,000 chips, which is just not practical. So realistically, we believe that maybe in the next 10 years, next 3 years, sorry, that there's probably maybe another 10x improvement in the number of chips within a cluster. Maybe you can get up to 10,000 chips. But not much more. And so what that gives us is a path to about a 60 times gain in performance. But the ML industry is looking for 1,800 times. And that is ultimately what we call the grand ML challenge in front of us. We need to find ways to improve process gains, architecture gains, and improving scale out. And so imagine a world where not only can you get the Moore's law 2x in process, but you can get 20 to 100x performance improvement in process, right? Not only can you get a 3x improvement on architecture, but you can get up to 100x or 150x improvement on architecture. And then, of course, you still need some level of system scale out. And that's the future that we at Cerebras are embarking on. And so the natural question is this possible? We think it is, but only if you have some out-of-the-box thinking with co-design. And today, I'm going to just outline a couple of the things that we've done at Cerebras to address this very first one, which, as we all know, is about Waferscale integration, I'm sorry. So over the past several decades, Moore's law has been amplified traditionally by building larger and larger chips. This is a plot showing die size, or the size of each chip, over the last 4 decades or so. And as you can see, there's a steady increase. Unfortunately, that is basically flattening out now. And the main reason for that is because we have challenges in yield, lithography, and power and cooling of these larger chips. Now, we as an industry have been doing some remarkable things to try to get around that die size limitation with advanced techniques like chiplets or MCMs. We're seeing upwards
MCM,
of multi-chip modules. So these are individual chips that are tied together in a single package. And we're seeing maybe on the order of 2 to 5 times larger chips. And just recently, as some of you guys may have seen as well, we were very encouraged by some of the early announcements by Tesla, who have built a very advanced interposer where they've placed 25 smaller chips together, and that's getting them about 10 to 20 times larger chips in terms of silicon area. But at Cerebras, we think that we can take this yet one step further. And a couple years ago, we announced our first Waferscale engine. And just a few months ago, we announced the second generation, which is 56 times larger than the largest traditional chip. Here's a picture of it. Here's one for real. It's the size of a dinner plate, basically. But it's a single piece of silicon. It's a single chip. It's over 46,000 square millimeters in size, 2.6 trillion transistors. Right? These are just mind-boggling numbers on a single device. And with all of that silicon resource, we can achieve some truly remarkable performance on this chip. Now, to do this, we need to solve those 3 fundamental problems that I just mentioned. And so let me just quickly walk you through how we approach this. The first is yield. Defects in manufacturing are always going to be there, even in mature processes. And so this is traditionally one of the main reasons why larger chips are harder to build, because you get more defects. We've addressed that by leveraging a very uniform architecture on the chip. So we have redundant cores, and we have redundant fabric links, where whenever we detect a defect, we can actually use the redundant core and take the place of the defective core, and then use the fabric links to reconnect it all so it still looks like a logical faux fabric. Now, as you can probably see already, this is only possible with co-design with the chip architecture. The next area of innovation is we need to work around the lithography limitations. Building chips is basically a lithography problem. You're flashing light through a reticle, and there are physical limitations to how large that reticle is. And so what we've done is instead of trying to push that envelope, which has some fundamental limitations, we work within the existing manufacturing process where these individual die are essentially printed on the wafer. But instead of cutting them all up and making really small chips, we cut out the largest square that we can on the wafer, and that becomes the full large chip. This is done with very tight collaboration with the fab, which is TSMC in this case, where we then add small wires to bridge the gap between these otherwise independent chips on the wafer. And as you can also see, this is also only possible with very tight co-design. In fact, the entire fabric architecture that we have on the chip was designed in concert with this fab process. And then lastly, I guess before we move on, just to quickly illustrate, these little wires that I showed that are bridging all of these otherwise independent chips. These little wires are a really, really big deal. And the reason is because they provide the same performance that you could get within a single chip, but across the entire wafer. And ultimately, it really is just physics, because traditionally, the way you connect together many, many small chips is you go through a printed circuit board, you go through connectors, maybe even cables. And it turns out that driving bits less than a millimeter on silicon is much, much easier than going through all of that traditional infrastructure. And you can see some of the numbers here. By doing the interconnect this way, we can get almost an order of magnitude higher bandwidth per square millimeter of silicon, and almost 2 orders of magnitude higher efficiency, because it's just physics. It's just much, much easier. Now, It's easier on the device to drive these bits such a short distance, but in some sense, what we've done is we've pushed that complexity into the package. The package is the mechanical structure that holds the chip together. And so let me talk about some of the challenges there and how we overcome those. And the main purpose of the package is to power and to cool the chip. And because of the sheer size of the wafer, traditional ways of cooling and powering just wouldn't work. The heat density and the power density are just too high. If you use those traditional methods, you really only would be powering and cooling the edges of the chip. And so the way we work around that is we basically flip the power and the cooling 90 degrees, and we use the third dimension, and we bring the power perpendicular into the chip directly from the backside of the printed circuit board, and then we take the heat out again perpendicularly using water cooling. And as you can probably already imagine, this is only possible if it's co-designed with the system. And sometimes we joke about this, and we say, imagine if we took this and we brought it to a Dell and asked them to build a server around it. It just isn't possible. It has to be designed together with the system. And so the way that looks is, I'll wrap up in a minute. And the way that looks is we start with the wafer. We surround it with what we call the engine block, which is what's bringing the power and the cooling in. And then the power comes in perpendicular in the front, the heat goes out the rear. And then ultimately, we build the system around this engine block. All of it is to support that wafer with power supplies, water pumps, heat exchanger, and all of that. Power in the front, cooling in the rear. And finally, this is what the system looks like. And this is my last slide. So perfect timing.
The person who really introduced me to this, to the great gains that are being made and possible in recent years in overcoming the scandal of microelectronics is Pierre de Rochemont of Frontier Nanosystems, and he's got lots of ideas of how to tame the sprawl of wires and resistors and capacitors and that occupy most of the space on printed circuit boards, even as we move to nanometer geometries. Thank you.
And wasted heat. There's a lot of wasted heat. So do I push a button here to get it? There you go. So our technology, I'm here to affirm what Mark Mills hinted at earlier today, is that we had amazing technologies that were created in the 1980s and have been held back from the market. Our technology was originally created under Ronald Reagan's strategic initiatives. And if you really knew, if you're working in the program, you knew that the main purpose of those initiatives were to scare the hell out of the Russians, which he did, but also to recapitalize the United States around industrial drivers, major industrial drivers. Because the people running the country knew that silicon was going to be fully commoditized by 2010. So the two drivers that I was involved with was creating superconductors that could be cost competitive with copper wire. In the 1980s, 86, IBM discovered these ceramics that were very, very complex. And when I say complex, they weren't commodity materials. You look at commodity materials, they have one element in their structure, copper or silicon. You look at silicon from a performance perspective, it's really a lousy semiconductor. It has thermal problems, and its electrical performance is largely unimpressive. But it's the cheapest and easiest to make, and it set the cost standard for future profitability of the entire industry. The superconductors that we developed had 6 different elements in them. Right? In order to make those, you had to make those reliably, and you had to achieve a property known as atomic scale chemical uniformity. That ability to make it atomic scale chemical uniformity, which means we deposited a layer And everywhere we looked, we had the same composition, no matter what the volume was. And that capability gave us the ability to create a new phase of matter we call Big Nano. Big Nano will revolutionize multiple industries because it allows humans to interact with the quantum world. We're not talking about quantum properties confined to a narrow channel somewhere on a chip. You're talking about materials that are big enough that for humans to touch and manipulate and interface with that exhibit those quantum properties. So when the drivers that were going to bring superconductors into the market were scuttled, it's bipartisan scuttling. George H.W. Bush killed the superconducting supercollider that was going to be bigger than CERN and placed in Texas. We spent more money filling in the tunnels than we would have spent finishing the project. And the project that I was involved in was something called MagLifter. In the wake of the Challenger explosion, the concepts that NASA was advancing was to take the shuttle off the giant fuel tanks with exploding booster rockets, put it on a magnetically levitated sled, and use electromagnetic propulsion to slingshot it up the side of a mountain. If you could get it going 600-700 miles an hour and have it separate from the track at an altitude of 14,000, 15,000 feet, all you needed were small rockets in the tail of the shuttle. So if you guys are wowed by SpaceX, I can tell you, that's incremental as opposed to order of magnitude gains in economic efficiencies. So in 1996, as MagLifter was scuttled, I was brought down to the Naval Research Laboratory, and I was told, the American people need you. You have a great technology. We're sorry the drivers are scuttled, but you're a smart guy. You'll find other purposes for it. And I was left on the wayside. Now, the other thing that they told me, they said, stay away from government. Imagine having a government that's honest enough to tell you to stay away from it. But that's what we had. And one of the guys, it took me a long time to figure out, to introduce new technology, you really have to focus on market drivers. You can have the world's greatest technology, it's going to sit in the lab. You have to look at what gets technologies adopted. So one person who influenced me was Dan Rose. Dan Rose brought out the crash scenario for the silicon industry in 1996. He was badgered out of the industry, but essentially what he did is he looked at the end user markets. So the top line is the logarithmic chart of the growth of systems, medical systems, military systems, all the revenues that were generated by these systems, consumer, telecom. And he looked at, in the early 60s, these were largely vacuum tube systems. And you can see that the chip, created great market value by cutting into that revenue. So by the 1970s, 2 cents of every dollar spent on a system went to chip manufacturers. And Dan simply pointed out the rationale is by 1995, it got to 20 cents, and there was no way this growth could be maintained because the chip manufacturers would say, well, our value of chips will outgrow the value of the systems. No way. And he considered that all chips could ever get was 20 to 30 cents of that end user market. Let me see. All right. So what we have is basically an industry that has been managing itself out of existence, right? Because if we had the robust growth in the end user market of 7%, we should have had a 4 trillion market today. We don't. What we wound up in 2017 was a market that is tinier than had been projected. And in fact, we have managed to cut the end user market by 65%. Right? That's not smart thinking. It's not thinking at all, from what I can tell. And if you look at the growth of any market as the pulse of the market, we've killed the patient. We're looking at markets that actually have negative growth. These are shrinking markets. So what is really needed, and if you were to look at what really happened in the market, we forgot that every technology has a life cycle. And we just thought, well, there would be no end to the silicon life cycle. Well, there is an end to the silicon life cycle that involves putting silicon on printed circuit boards, and I'll go through that. Right? So what we need is a new paradigm. And I'm going to point out that the silicon market was $100 billion in 1995. And if I take in inflation-adjusted terms, the market today of $200 billion is no different than the $100 billion spent in 1995. We're not thinking. So why are we not thinking? Who mandated this insanity? And you can see that the Frankfurt School has penetrated into business, right? And it's very authoritarian. So the decisions were made, well, the chip has all the value. We're only going to change a computer design when there's a new innovation in chip architectures. If you were working on boards or packaging, you could only introduce your technology when there was a major change in the chip. We changed a node. And if you were working on passive components, which are these half-cent things, forget it. You'll never be allowed. No innovation in passive circuitry would ever introduce a change in computer designs. Well, that's what we focused on with the technology. Because if you look at business operations and even finance and ways to design, you find that the passives were creating all the bottlenecks in manufacturing, the bottlenecks in performance. So to show you what we mean, we've been able to shrink the size of transistors. With every transistor shrink, we can increase the speed of the chip. Right? But the moment you put that chip on a board to interface with the passive circuitry, you're throttling its clock speed down. Has anybody bought a system, a computer system that operates faster than 2.5 gigahertz in the last 15 years? It ain't there, because the commodity materials in the boards, right, distort the higher frequency signals that that shape the digital pulse. Right? You can get some marginal gains, right, if you start stacking, but ultimately the stacked chip assembly has to interface with the board. So what we allowed with Big Nano was to create passive semiconductors that have ultra-high performance, which means you shrink them, right? They will not distort. Big Nano will not distort the higher frequency signals because you're looking at the quantum property rather than the bulk property, right? And this satisfies critical performance tolerances that Nokia mapped out in the 1990s. You have to have every passive component have exactly the same value within the material, right? And that value cannot change with temperature or time. Big Nano is the material that gives you that. Right? And so this allows systems now to start running at the speed of the chips in the stack. So here you go. Once again, you see the value of this technology. We can, the chip created enormous market value by shrinking the size of a transistor from a vacuum tube to microscopic dimensions and assembling them in large numbers in a single part. Today, we can put billions of transistors into a single part, but the passives around it are going to occupy 5 times the footprint. Right? But the entire system is the passive circuitry. The real value in the system is both the passives and the transistors, the passives and the active circuitry. So we've been looking at things purely from a banker perspective, right? Oh, printed circuit boards are cheaper. Yes, from a bill of materials cost. But if you're an operations guy, you know that the cost of goods sold is the thing you really have to be working on. We ignore that, right? We can make materials that shrink the size of the passives, but they're extraordinarily expensive using traditional techniques. And there's this gap between the size, the dimensions of the chip and the dimensions of the transistors. So our ability to make ultra-high performance electroceramics shrinks the size of the passive components to the point where those 48 passives that are there can be integrated on 2 chips, one that sits above or one that sits below. Right? Big Nano and the speed at which we can do it, right, gives us the price breakpoint. So if I were to use atomic layer deposition, right, which is the standard right now, and I wanted to put 100 micron film down, it's going to take me 11 years to do that. But with our technology, that's done in about 25 minutes. And this gives us, and it's done at temperatures that will not damage transistors in the chip. So this gives us the ability to fully integrate the system. Now, if you do that, you can start creating new designs that shift this to this, right? And you can start, as opposed to integrating everything onto a chip, because there's a corollary, there's a backfire to Moore's law, right? Is that the smaller you go down in technology node, the more expensive it becomes. And it becomes more and more expensive when you start adding different functions like memory and different types of processors. So by doing this, you find that you get rid of most of the passives because they're needed for the board. They're not really needed for the chips. You don't need that many of them, right? And you can start making modular circuit designs. So if you look at a market like wireless infrastructure where you may need a lot of memory in a cell tower, but you don't need that much in the Pico towers that are mostly used these days, you can use the same design and just swap out the number of memory chips needed in the stack. The other thing, when you can start integrating, so this gives you design scalability. When you can start integrating passives with actives, you can come up with power switch designs that switch large currents at arbitrarily high speed And the loss in the power switch is the conductors. Right? You can eliminate everything. So now you can start integrating power very close to the active circuitry. Right? This allows you to eliminate cache memory, major power hog. Because if I can switch and if I can move data at the same rate that the clock speed of the processor operates, I don't need cache. I can now take state machine functionality that's used in AI and give it general purpose because I can stop the flow of data, reroute things when a higher command comes in, and create the great advances that Cerebras is talking about in general purpose computing environments.